Today, disasters are more complex, more costly, and more unpredictable than ever before. Traditional methods are no longer enough to understand emerging threats or to protect our communities. We need the ability to see what is happening, where it's happening, and who will be affected, in real time. Geographic Information Systems, or GIS, give us that ability. With location intelligence, we can visualize risks, understand vulnerabilities, and make faster, more informed decisions. Before a disaster, GIS helps us identify critical assets, analyze hazards, and prioritize mitigation projects. When a disaster strikes, GIS provides real-time situational awareness, helping teams coordinate response efforts, deploy resources where they are needed most, and communicate clearly with the public. After the event, GIS guides recovery by tracking progress, documenting fieldwork, and ensuring transparency. In this module, we'll explore how GIS transforms disaster management from reactive to proactive, from simply responding to threats, to anticipating and reducing their impact before they occur. By the end of this module, participants will understand how GIS supports proactive disaster preparedness. They will learn how to locate vulnerable assets and identify potential hazards using spatial analysis, allowing them to see relationships and risk patterns that are not visible in traditional reports. Participants will also learn how to prioritize mitigation projects through data-driven decision-making, ensuring that limited resources are directed to areas where they will have the greatest impact. Finally, they will learn how to use maps as a communication tool, enabling clearer collaboration between stakeholders and improving overall community preparedness. Disaster resilience means a community's ability to anticipate, withstand, and recover from disasters by understanding vulnerabilities and planning effective actions. Risk and hazard mapping known or potential hazards to understand where threats exist and how they may impact communities. Vulnerability and exposure analysis. Identifying populations, infrastructure, and assets that are most at risk when a hazard occurs. Scenario and impact modeling. Simulating possible disaster scenarios to estimate damage, impact, and response needs. Critical infrastructure mapping. Visualizing key infrastructure such as hospitals, utilities, transportation networks, and lifelines to protect their continuity. Resource optimization and prioritization. Allocating limited resources to the highest risk areas based on data-driven decisions. Real-time data integration. Incorporating live data, weather, field reports, sensors, into maps for immediate situational awareness. Preparedness communication and stakeholder engagement. Using maps and dashboards to share plans, coordinate actions, and ensure collaboration among agencies and community members. Disaster resilience is about helping communities not just survive disasters, but recover stronger. To build resilience, we must continuously understand where communities are vulnerable and what needs protection. GIS helps us do that by mapping hazards, demographics, and critical locations so we can design effective mitigation strategies. As disasters become more frequent and costly, identifying the right problems and choosing the right actions becomes essential. Every community is different. GIS gives us the insight we need to tailor solutions, especially for vulnerable or underserved populations. Awareness. GIS allows us to see what is happening and where. We visualize hazards, vulnerable populations, and critical assets on a map. Analyze. Understanding. We evaluate risk levels, model scenarios, and measure possible impacts. GIS helps reveal relationships and patterns that are not visible in static reports. ACT, Planning and Preparedness. We transform insight into action, optimizing evacuation routes, prioritizing projects and placing resources where they will have the greatest impact. GIS turns uncertainty into clarity, and planning into preparedness. Being prepared for disasters today is more than just a necessity, it is a safety shield for resilient community. We all know that events like floods, earthquakes, or wildfires can, unfortunately, be right on our doorstep at any moment. So, how prepared are we for these major events? The answer to this question lies within Geographic Information System, GIS-based simulation environments. Using this technology, emergency management teams can now model risky scenarios in a virtual setting, without any risk of casualties or property damage. These simulations provide us with three priceless, critical advantages during the preparation phase. Evaluating response plans. We test our existing response plans in this virtual environment, seeing with concrete data which steps are effective and which are not. Optimizing evacuation routes. a critical issue during a disaster. We evaluate evacuation routes, identify bottleneck areas, and determine the fastest and safest paths. Strengthening interagency coordination. By having different agencies, firefighters, health, law enforcement, etc., work within the same virtual scenario, we elevate interagency coordination to the highest level before the event even occurs. What do we gain from these virtual drills? We essentially achieve three main outcomes: increased readiness level. Our teams repeatedly practice decision-making processes without the stress of a real crisis, thereby significantly increasing the level of readiness. Reduced uncertainty. Since what will be faced during critical moments is seen more clearly, uncertainty is reduced, and teams can act more calmly. Faster and more informed decisions. Ultimately, when an actual disaster happens, these virtual experiences enable management teams to make faster and more informed decisions, maximizing our capacity to save lives. GIS-based simulations are not just a tool in disaster management, they are a life-saving philosophy of pre-preparation. Using GIS simulation environments, we can model different disaster scenarios in advance, in a safe and controlled setting. These simulations help us understand possible impacts, explore different decisions, and evaluate the consequences before a real event occurs. In the next slides, you'll see how this capability adapts to different hazard types, each with its own planning needs and data requirements. In this presentation, we will explore 4 real-world case studies showing how GIS and location intelligence strengthen disaster preparedness. Taiwan uses 3D simulations to plan flood response. Arizona firefighters manage field operations through mobile apps. Alabama monitors tornado sirens in real time, and Lithuania simulates nuclear accident scenarios to predict impact and plan ahead. The common theme: location intelligence empowers better decisions when every second counts. Taiwan is an island of approximately 14,000 square kilometers, with tropical and subtropical climate conditions, which makes it naturally vulnerable to heavy rainfall and flood hazards. To better manage this risk, the National Science and Technology Center for Disaster Reduction, NCDR, developed the Flooding Wargame Simulation Platform, training and emergency response, approaching flood scenarios with a military-style exercise mindset. The workflow of this platform is built around 3 key components: an optimized 3D model experience, creating a realistic digital twin of the city, a fast, easy-to-use platform, enabling users to define flood scenarios with just a few inputs, 3D visualization, helping emergency teams clearly understand impacts and support decision-making. This approach allows flood scenarios to be modeled safely before an event occurs, enabling emergency teams to make informed decisions during the planning stage. On this slide, you see how the Flooding Wargame Simulation Platform is used to analyze a real location, Guishan Elementary School. To enable this level of analysis, the team first created an optimized 3D model of the city. Using ArcGIS Pro, they combined building footprints, building heights, terrain, and elevation data to generate realistic 3D visualizations of each structure. Once completed, the model was published through ArcGIS Enterprise, and an application was developed on the ArcGIS platform so that teams can easily access and interact with it. The second key component of the platform is its fast and easy-to-use workflow. The user simply selects a spatial area, sets the starting point of the flood, and enters the estimated water depth. Within seconds, the system calculates which low-lying areas would be affected and which buildings or populations fall within those zones. In this example, around Guishan Elementary School, the system automatically identifies potential hazard zones and displays the results as thematic 2D maps, including flood-affected areas, vulnerable groups, evacuation shelters, rescue resource networks, and even the locations of heavy construction equipment and relief agencies. This enables emergency teams and school administrators to plan ahead. They can determine safe evacuation routes, where to position resources, and how to protect vulnerable students and staff before a real flood occurs. In the final stage of the simulation, emergency teams are able to view the flood scenario in 3D. The platform combines the digital terrain model, satellite imagery, street maps, and 3D building models. In addition, live CCTV feeds from across Taiwan are integrated, allowing teams to monitor the situation both on the map and through real-time video. This 3D environment enables fast communication and strong coordination among field teams. Building damage, flood depths, traffic restrictions, and viable rescue or evacuation routes can all be evaluated from a single screen. The system also highlights vulnerable facilities. For example, elderly care institutions are displayed on the map, and those with ground floor exposure are specifically flagged. This helps social welfare organizations assess their risk and prepare in advance. The image on the slide shows how Guishan Elementary School was affected when Typhoon Sotalor struck Taiwan in 2015. The satellite imagery shows the school before the disaster on the right, and after the disaster on the left, completely covered in mud and nearly inaccessible. Image courtesy of Guishan Elementary School. These simulations and preparedness efforts enable Taiwan to respond far more effectively when major floods occur, reducing impact, protecting lives, and safeguarding vulnerable communities. The Northwest Fire District serves more than 110,000 residents. Their work depends heavily on having reliable infrastructure, especially fire hydrants. Instead of paper forms and manual reporting, the district shifted to mobile GIS apps. Creating confidence in hydrants, nearly 10,000 hydrants in the district are tracked in real time. Their status, location, and associated water utility are visible instantly, giving teams full confidence that the hydrants will work when needed. Making infrastructure inspections digital, field crews use mobile apps to capture hydrant inspections directly from the field. In just 60 days, one team inspected 4,000 hydrants, a task that used to take much longer on paper. Creating an app for everything. After seeing how effective mobile GIS could be, the district expanded the approach and developed more apps, from tracking hydrants to building pre-incident plans. Everything that used to be manual is now digital, accurate, and accessible. On the left, you see firefighters inspecting hydrants. Every hydrant is checked annually, and the operational status is recorded directly into the mobile app. No paper, no delays. Data becomes instantly available to commanders. On the right is an interactive floor plan from the Pre-Incident Plan Locator app. This prototype gives firefighters visibility before entering a building, showing doors, hazards, equipment locations, and escape paths. In smoky or zero visibility environments, this information can literally save lives. Tornadoes are a serious threat in Tuscaloosa County, Alabama. To protect the community, the county's Emergency Management Agency, EMA, is responsible for operating the outdoor warning siren system. In the past, siren information was scattered, stored in spreadsheets, PDFs, paper files, and different GIS formats. This made it difficult to track maintenance, verify locations, or ensure that sirens were working. To solve this, EMA modernized the entire workflow using ArcGIS and mobile field apps. Siren locations, attributes, inspection status, and maintenance history were consolidated into a centralized GIS system. Field teams can now update data directly from the field, and managers can monitor siren status in real time. By bringing all siren data together and digitizing inspections, the agency increased reliability, improved response readiness, and strengthened the effectiveness of tornado early warning systems, especially when it matters most. This visual represents the transformation in how the agency manages its outdoor warning sirens. Siren data is now stored in the application built within Lucity's Enterprise Asset Management System. Each siren feature in the GIS is directly linked to its related maintenance work orders and cost estimates. Previously, information such as siren location, maintenance history, and operational status was kept in separate Excel files or paper documents. This often led to data loss, slowed down maintenance workflows, and made reporting more difficult. Now, through a single system, the agency can see in real time the exact location of each siren, the date of the most recent maintenance, the schedule for the next maintenance, the associated maintenance costs. This integration enables the agency to manage its siren infrastructure more efficiently, reduce maintenance costs, and ensure that the early warning system is always operational when it matters most. This visual shows the technology used during field inspections. Using the Survey 123 application, field specialists can view the siren's exact location on the map while simultaneously entering inspection information for that siren. With this integrated workflow, location verification, operational status, surrounding obstructions, such as vegetation, and other risk factors can be recorded directly on site. As a result, agencies improve data quality and make inspection and maintenance processes faster and safer, increasing the overall reliability of public warning systems. Lithuania conducted a 4-day full-scale nuclear accident simulation, placing ArcGIS at the core of the operation. Because responders were using technology they were already familiar with, all agencies could work together seamlessly, seeing the same information on a shared map and forming a common operating picture instantly. Real-time field updates, visual dashboards, and plume maps provided current, actionable information, helping decision-makers choose evacuation routes and allocate resources based on facts, not assumptions. The exercise demonstrated that Lithuania is ready, coordinated, informed, and capable of responding effectively in a real nuclear emergency. With GIS integrated into the simulation, Lithuania can model the potential spread of a radiation plume and estimate which communities could be affected in the event of a nuclear accident. The system analyzes real-time meteorological data, such as wind direction, temperature, and precipitation, to predict the impact zone. This allows authorities to identify populations at risk, determine which areas may require evacuation, and prioritize where emergency resources should be deployed. Instead of reacting after the impact, decision-makers can make proactive choices. Evacuation routes can be planned earlier, public warnings can be issued sooner, and response teams can be positioned strategically. In other words, GIS not only shows what is happening, it helps predict what will happen next. During the drill, the Lithuanian government streamlined several emergency processes, especially how real-time information from the field was collected. Teams could now use mobile apps to submit location-specific observations, status updates, and measurements directly to the shared GIS environment. This eliminated delays that typically occur with paper-based reporting and established a continuous flow of real-time situational data. Field crews marked radiation readings, evacuation points, and hazards directly on the map, while command staff viewed the updates immediately and made informed decisions. As a result, operations became faster, more transparent, and far more reliable. As the exercise progressed, participating agencies relied on maps and dashboards that displayed real-time, shared information to guide their decisions. Field updates from various teams instantly appeared in the unified system, allowing decision-makers to monitor impacted areas, prioritize response actions, and allocate resources efficiently, all from a single operational view. This shared data environment accelerated decision-making and strengthened interagency coordination. Regardless of their role, every team was working from the same understanding of the situation, which made the response more organized, more efficient, and ultimately more effective. As we bring this topic to a close, a few key themes become clear. Throughout this module, we saw that GIS is not just a technical tool, it is the backbone of effective disaster response and recovery. When chaos unfolds, GIS gives us clarity. When decisions must be made within minutes, GIS provides real-time awareness. When resources need to be coordinated across agencies, GIS creates a single operational view everyone can trust. We also saw how accurate, location-based workflows strengthen both damage assessment and debris management, two of the most critical steps in rebuilding a community. And across every phase, information sharing remains essential. When all stakeholders work from the same map, the response becomes faster, fairer, and far more coordinated. The overall message is simple. GIS helps communities recover not only quickly, but more resiliently, with transparency, trust, and data-driven decisions guiding every step.